Hi, good day. My name is Javed Mohammed. My group consists of Vikash Rampersad and Sadanand Lochan, and today we will be presenting a water wheel design. My group and I have been asked to design a water wheel using the concept of a river in the northern range due to flow rate from the river, which can be inconsistent depending on the seasonal rainfall. We have decided to include a holding tank that will maintain a fairly constant water level. Water from this tank will then fall onto the wheel to generate electricity. There will still be fluctuations due to the flow rate of the river. A control valve will be used to maintain a constant power output. We will be building a prototype that will physically simulate this system. Introduction. A water wheel is a type of device that takes advantage of flowing or falling water to generate power by using a set of paddles mounted around a wheel. The falling force of a water pushes the paddles, rotating the wheel. This rotation of a wheel can be transmitted to a variety of machines through a shaft at the center of the wheel. These wheels are generally large and composed of wood or metal with many blades or buckets along the edge of the wheel to capture the power of the moving water. Type of water wheel used in this project design. Overshoot wheels can be built if there is a significant high drop in the river or body of water being used to move the wheel. Generally, these are built on the side of a hill as a drop of at least 4.5 meters. In this type of water wheel, the water exits a flume above the wheel itself. The water then falls down into the blades of the water wheel, pushing the wheels forward. The fact that water is introduced at the very top of the wheel means that water falls the greatest distance, making it highly efficient. Conceptual design. Here is a list of all the materials used to construct our prototype. We have a holding tank of 17 liters, a collecting tank of 50 liters. The wheel is a 4-inch radius, recycled bicycle rim. Paddles used were wooden pallet sticks, 4 inches in length. 8 pallet sticks were used. A frame was built to support the wheel, 24 inches in height, 5 inches in width. A submersible pump was also used. Hose lines connected to the submersible pump. Bearings were placed on the frame to support the shaft of the wheel. 3 3/4-inch male PVC adapters were used. 1 3/4-inch ball valve and 1 3/4-inch elbow. Here we have a schematic showing our prototype. On the top we have the 17-liter holding tank connected with PVC attachments. We have the 3/4-inch ball valve also connected and PVC connections directed above the water wheel, placed directly onto the paddles of the wheel. This frame was placed in the collecting tank. The submersible pump was also placed in the collecting tank, and the return line was connected to the submersible pump and returning into the 17-liter holding tank. We're now going to show you a video of this prototype.
Good day, my name is Sadanand Lochan, and today I'll be going through how we calculated theoretical results of our project here today. So our first equation is based on the resistance of the valve, where the resistance of the valve is equal to the change in height all over the output flow rate. So we could change this formula, rearrange it for the output flow rate to be on the subject of the formula. So the output flow rate will be equal to the change in height all over the resistance of the valve, and that will be our equation 1. Our equation 2 is based on the capacitance of the tank, where the capacitance of the tank is equals to Qi, which is the input flow rate, minus Qo, which is the output flow rate. So we substitute equation 1 into equation 2, we get this equation right here. And if we take Laplace and rearrange the equation, we get our final fluid system equation here. Next up, we have our linking equation, where the output flow rate all over the cross-sectional area of the pipe is equal to the radius of the wheel multiplied by the angular displacement. So we can change this equation in the terms of H. So H is all over the cross-sectional area of the pipe multiplied by the resistance of the valve is equals to R, which is the radius of the wheel multiplied by the angular displacement. So now we try to make H the subject of the formula, and we take Laplace. So while taking Laplace, we get this equation right here, and from this equation, once we rearrange it to our liking, we get our desired transfer function. So now, since we have our desired transfer function, we will now have to calculate the different variables we have within our transfer function. So first off, we have the resistance of the valve. R is equal to H over Qo, where Qo, our output flow rate, is equal to the volume of our tank, which is 17 liters, all over the time it takes to fill the tank, which is 219 seconds. So you get 0.078 liters per second. And our change in height 1 and height 2, is 0.381 meters minus 0.28575 meters. You will get 0.9525 meters. So our resistance of the valve is equals to the change in height all over the output flow rate. You'll get 1.2212. Then we also have the capacitance of the tank. The capacitance of the tank is equals to pi r squared, where r here is equals to the radius of the tank. So it's pi by 0.1143 meters or squared. You get 0.0410 meters squared. And then we get the cross-sectional area of the pipe. Again, A is equals to pi r squared. So r here is equals to the radius of the pipe. So it'll be pi by 0.0127 squared. So you get 0.0005 meters squared. So here we are talking about our step unit increase. So throughout our calculations, we have an estimated value of the first step unit increase of 100 milliliters per second, and we change it up a little bit so that we could use it here. It will be 1.0 by 10 to the minus 4 meters cubed per second. We take Laplace of this unit step, then we substitute it into our transfer function, and we arrange the transfer function so we just have our angular displacement as our final thing here. And we can also further substitute this, further simplify the equation by substituting the time constant with the time constant tau is equals to RC. Substituting the time constant, we will get theta, which is the step unit increase, and the angular displacement. We simplify the equation, and now after taking the Laplace inverse, the step unit equation is, let me show you here. And now from that we could get our theoretical results. So we take our theoretical results for TS, we substitute the time from 0 to 20, and we use our angular displacement here for the unit step increase of 100 milliliters per second, 200 milliliters per second, 300 milliliters per second, and here we get our final theoretical result. So now I will pass you over to Vikash Rampersad. He will give you the rundown on our actual results we gained in this experiment. Thank you.
Good day everyone. My name is Vikash Rampersad, and here I will discuss the actual results for our experiment conducted. The formula below Qi equals V1 over T, where Qi is the input flow rate, V1 is the volume of the holding tank, which is fixed, and T is the time taken for the holding tank to be filled with liquid. The next formula is angular displacement, equals to the number of rotations N multiplied by the circumference of the wheel C and divided by the radius of the wheel R. Now we have our results tabulated below with the values of the number of rotations for the first step increase of the 3 time intervals 10, 15, and 20 seconds. Using the same results obtained from the table, we then went on and calculated angular displacement using the formula given for the 3 different time intervals 10, 15, and 20 seconds. Now I'll end this presentation of our water wheel group design project with the 4 main factors that affected us when measuring results. Weather conditions were not stable, input flow rate not consistent, valve resistance, and human error. Here are 3 pictures of the group members that conducted this project. Thanks for watching.